Dear students, in this module we shall study about carbenes and nitrenes. Carbenes, we will discuss about their structures, the reactivity, behavior of specially talking about the methylene carbene, and we will consider some examples where carbenes are involved as intermediates. After that we shall study about nitrenes, know what are nitrenes, and we shall try to see what are the difference between carbenes and nitrenes and consider some reactions involving nitrene as the intermediates. After studying this module, dear students, you shall be able to identify the basic structure of carbenes as well as nitrenes. You shall be able to know what are the methods to generate these carbenes and nitrenes and evaluate the reactivities of both carbenes and nitrenes. And you shall be able to learn about some important named reactions which involve the carbenes and nitrenes to yield the products of industrial and chemical importance. Let us begin with the detailed study about the carbenes. Methylene, that is CH2, can be considered as the first member of an alkene series. Methylene as a highly reactive transient molecule was first proposed in 1930 by Penzic technique, that is removal of metallic mirrors. Its existence as a definite intermediate in certain reactions was proved in 1959 by spectroscopic methods. Not only CH2 but RCH, R2C type of carbenes have been investigated after that. Carbene chemistry was one of the topics most intensely studied if we talk about during 1950 to 1960, a decade, and then again between 1990 to 1994. The word carbene is used for methylene and as a general term for all similar compounds. If we talk about its structure, carbenes are highly reactive species and practically all have lifetimes considerably less than 1 second. With exceptions noted, carbenes have been isolated only by entrapment in matrices at low temperature, that is 77 Kelvin or less. Carbenes are divalent carbon compounds with 2 non-bonding electrons on one carbon, that is in all 6 electrons on carbon. The nature of bonding, if we talk about in carbenes, this has been analyzed by molecular orbital calculations by various approaches, and there are 2 important possibilities. That is, we can have the singlet carbene, where you can see the structure as shown here, where both these unpaired electrons are there in the same orbital, and here the angle is about 105 degrees. On the other hand, you may have one possibility which is triplet, and in this structure you can see that these 2 non-bonded electrons are in separate orbitals, and here it is more like the alkyne nature, more linear in terms of HCH, but the angle HCH is about 135 degrees, it is not exactly 180 degrees. So, looking at these structures again, the singlet carbene, you can see the HCH is more angular, the angle is about 105 degrees, and in the triplet it is more linear, the angle is about 135 degrees. The 2 non-bonded electrons of a carbene can be either paired or unpaired, as we have seen. If they are paired, the species is spectrally a singlet, and hence the name given to it, it is singlet carbene. While 2 unpaired electrons, if they are inseparate, then it appears as a triplet, and hence the name triplet carbene. The designation singlet state and triplet state refers to the molecular electronic states. In the singlet carbene, the carbon is sp2 hybridized. The non-bonding electrons, they have anti-parallel spin, that is the electrons are paired in terms of this spin. The triplet carbene on the other hand has two unpaired electrons in separate orbitals, and the carbene center in triplet carbene is sp hybridized. The non-bonding electrons have parallel spins in different orbitals. The ground state energy difference, if we talk about between the singlet carbene and the triplet carbene, it is calculated to be about 10 kilocalories per mole, where triplet has lower energy and singlet has higher energy. On the basis of this, one can say that singlet methylene should be diamagnetic and triplet methylene should be paramagnetic, that is as a diradical. Alkyl and dialkyl carbenes are generally triplets. Substituent carbene of electron pair donor ability tend to stabilize the singlet state by electron release into the vacant orbital, as you can see here. So, this X can be O or nitrogen or halogen, and through this lone pair, that is by the tendency to donate electrons, it can stabilize the singlet state. Talking about reactivity of carbenes. Carbenes, being electron deficient molecules, are obviously generally electrophilic. Singlet carbene is more like an electrophilic species, that is like R3C plus or the CO or the isocyanide. Triplet carbenes on the other hand, they behave like a radical. Both singlet and triplet carbenes are very reactive. Most of them are generated in situ, and there are no useful solvents to be used as media. They cannot be isolated, but their formation or involvement can be demonstrated by the product analysis. If we talk about the reactions, how they are carried out, most of these reactions involving the carbenes are carried out in gas phase or liquid phase. The reactions involving free carbenes are highly exothermic, and all the reaction of carbenes are generally fast, that is they have low activation energy. Let us now try to understand how these carbenes are generated. Diazoalkanes, we know they can be readily decomposed to carbenes by copper salts and other transition metals. The products of the overall reactions are the same as obtained by direct photolysis, and the general evidence suggests that an adduct of metal ion and carbene is involved, and this adduct you can see here as shown can be represented. So, here is the adduct which is formed, and this nitrogen, as it is removed from these diazothanes, then it will lead to the formation of the carbenes, and these carbenes you can see here, they will be as adducts with the metal ion. And this carbene adduct, we can see it can be written as shown here, where the CH2 is attached to this metal Ru, and in terms the Ru minus forms, and this will be giving the electrons to the vacant orbital in the carbene, and that is how there is the formation of Ru with carbon as a double bond. So, in this way the complexes can be treated as metal stabilized carbenes. A distinction is generally made between free carbenes and the metal ion complexes, and this later type are spoken as carbenoids. For example, the carbene generated by photosynthesis of diazomethane, where the N2 just goes, then it will be a free carbene. But the copper ion catalyzed reaction, it will lead to carbene coordinated to the metal, and that is where the carbenoid comes. And we can consider some other examples of carbene generation. So, the principle you can see that given a carbon with A and B, groups which can be removed. They can be same atoms, they can be different atoms or combination. So, the moment you remove A and B, there will be formation of carbene. So, they can be isopolar approach, which will be via photolysis, pyrolysis or the transition metal ion catalysis, and they can be polar approach where alpha eliminations occur to generate the carbene. Let us first try to understand the isopolar approach. Alkyl, aryl and acyl substituted carbenes from diazo compounds are formed under this category. For example, as you can see here, if you start with acid chloride and by treating it with base, you can have the formation of ketene by the E2 elimination, and this ketene when it is heated, there will be removal of this CO and it results in the formation of this carbene, which is R2C with 2 unpaired electrons. Then there is another example where we involve the diazerine. Starting from this molecule, by oxidation these 2 hydrogens can be removed and we get diazerine. And now you can see that this N and N can be very easily removed as nitrogen, and so this will be giving you the formation of this particular carbene. Another approach can be through epoxides. Starting from alkenes, you know, by treatment with per acids we can get epoxides, and these epoxides can further be broken into the formation of ketone and carbene. The other approach is the polar approach, that is the generation of carbenes via the alpha elimination or the 1,1,E elimination. Talking about this polar approach, the principle here is that R2C with H and X is there, and base will be doing this dehydrohalogenation, that is the removal of H and X, and as a result the remaining part of the molecule will give you this carbene. And what are the type of bases which are used? They are powerful bases like CH3Li, the potassium, tertiary butoxide, LDA, etc. they are required. Let us consider some examples. CHCl3 plus NaOH, this you have already encountered when you study the Riemann-Tiemann reaction. So, CHCl3 plus NaOH, it will give you first the CCl3 minus by the removal of H plus by OH minus, and then this CCl3 minus will remove Cl minus, thereby giving you this dichlorocarbene. Another example, as you can see here, this particular compound can be treated with CH3Li in the presence of THF, and further subsequently it will give you the formation of this R2C carbene. Now these type of reactions are not applicable if there is a beta hydrogen present, because then the alpha elimination will not happen, and rather the beta elimination, whereby you will get the alkene by dehydrohalogenation rather than carbene will be there. So this you have to keep in mind while looking for the formation of carbenes. Another case let us consider is the decarboxylation of trihaloacetates in aprotic solvents. As you can see here, we can start with this trihaloacetate, and in the presence of DMSO, further treatment there can be removal of MCl and the formation of dichlorocarbene, and obviously there is a decarboxylation which is happening in the way. Similarly, in the presence of water there will be first formation of CCl3 minus and followed by acidification that can go into further CHCl3. Another way is thermolysis or pyrolysis of trihalomethyl mercury compounds. As you can see here, this trihalo where you have 2 chlorines and 1 Br. So this trihalomethyl mercury compound, when it is subjected to heating around 80 degrees centigrade, it will go into thermal pyrolysis, that is pyrolysis or the thermolysis, thereby giving you dichlorocarbene and the remaining molecule as PHHgBr. And these mercury halides are covalent and stable at room temperature. Another example where you can start with trichloromethyl trihalosylane. If these are heated, then also it will lead to the generation of dichlorocarbene along with SiX3Cl. And these methods permit ready formation of carbenes in near neutral media. Another way of preparing carbenes is from carbonyl compounds, and this is a useful method to prepare carbenes from readily available carbonyl compounds. An aldehyde or a ketone is converted to paratoluene sulfonyl hydrazone, which is abbreviated or commonly called as tosyl hydrazone, as you can see here. And this tosyl hydrazone is then further treated with one equivalent of base at low temperature, and the base used here is NaOCH3 to form a salt of hydrogen, as you can see here. This salt is then decomposed in two ways. It can be done either by the use of UV light or with the help of heat beyond 130 degree centigrade. So, as a result you can see there will be formation of this carbene. And aprotic solvents such as DMSO, diglyme are essential to prevent the carbene reactions which may happen. So, this is how there will be formation of this carbene where the nitrogen will go out. The carbene generated leads to products, and this method avoids handling dangerous diazoalkanes. For example, you can consider this liquid, that this is the tosyl hydrazone with one equivalent butyl lithium, followed by heating you can generate this particular carbene, and this carbene will further give rise to these products where the major 38% is this one, and this 3 members derivative is less than 10%, and then 16% of this eliminated product. The first two compounds here are formed as a result of hydrogen migration, and the third, that is the double bonded by CH bond insertion to the methyl group. Let us now try to see the reactions which take place which involve carbenes in them. And what are the types of reactions we can encounter? They can be addition to double or triple bonds, insertion between the CH bonds and other bonds, and rearrangement. So, these are the broad categories. The outcome of the overall reaction depends upon the mode of formation, whether it is the singlet or the triplet nature of the carbene that has been formed. For example, you can see here what we mean by addition. If it is a CC double bond, then CH2N2 heating you will get carbene, and this carbene adds and you get a cyclopropane type of molecule formation. By insertion we mean, you can see here that this CH and this CH2 carbene can be singlet or triplet. It can get inserted between this C and H, and as a result you have in place of H CH3 coming in the product. In the rearrangement what happens is, as you can see here, starting from this, as the heating is provided beyond 60 degrees, N2 goes, you get the carbene, and then there can be migration of this phenyl or the migration of methyl, and correspondingly we may end up with these any of the products, that is this particular alkene in 50% ratio, then 9% of this alkene, or you may get this cyclopropane derivative in 41% yield. Let us try to know the behavior of these carbenes, especially talking about the methylene carbene. The chemical behavior of the CH2, that is the methylene carbene, is highly dependent on first the reagent, that is the precursor from which it is generated, second the wavelength of the UV light that has been used to generate, and whether the reactions are carried out in liquid phase or in gas phase. And another thing is whether the reactions are carried out in the presence of inert gas like nitrogen, argon, CO2, or gas like oxygen. The situation is complex and there are disagreements as to the exact interpretation of the facts. Methylene itself is the most indiscriminate reagent known in organic chemistry. It shows addition to double bond, triple bond, and even adds on to benzene, and is responsible for insertion into the CH bonds. For example, let us pay attention to some of these examples. As you can see here, given cyclohexene with CH2N2 or ketene used to generate carbene, we get this cyclopropyl derivative in 40% yield. And in addition to this, there is 25% formation of this alkene, 10% formation of this, and 25% yield of this particular alkene. Another example, take this cis-2-butene. When this is reacted with CH2N2 in liquid phase or high pressure, then there is the addition of the carbene to the double bond and we get major of the cyclopropane derivative along with other products. Similarly, look at this trans butene with CH2N2. Here also there is formation of major cyclopropane derivative and you can see the stereochemistry is retained. In cis, both the methyls are on the same side, but here both the methyls are on opposite as we had started. So, it is simply adding and you are getting the corresponding products. But the same cis butene and the trans 2 butenes, if we look at different conditions, let us look here. In the low pressure or inert gas conditions, we will get the mixture of cis and trans cyclopropane derivatives. Similarly, if you take the cis-2-butene and the trans-2-butene and we are trying to generate the carbene in the presence of copper, then it is highly stereospecific where there are no traces of the other. That is, from cis you get cis and from trans you get the trans product. So, highly stereospecificity is there. And if we talk about how to explain this, there is one view that hot methylene, high energy, high reactivity, low selectivity, low energy, low reactivity, high selectivity. And there is another view that singlet methylene and triplet methylene will take different routes. So, the scale hypothesis is single concerted step and the triplet carbene reacts in two-step radical pathway. And these hypotheses are applicable both to addition as well as insertion reactions. So, let us try to see the mechanism of addition by the singlet carbene. So, here you can see the singlet carbene addition. This is a concerted one-step process where simultaneously this carbene is adding and obviously here there will be retention in the configuration of what we have started. So, cis will give you cis, trans will give you trans. But if you look at the mechanism of addition by triplet carbene, which is radical pathway, as you can see here, starting from this alkene, there is first formation of this, then there is spin inversion and then there is the formation of this cyclopropane derivative. And at this stage the single bond rotation can happen and it will give rise to singlet carbene, and again if now the addition happens, from here there will be change in configuration. So, you get possibility of both the retention in the configuration as well as the change in the configuration. So, starting from cis you can get both cis as well as trans. So, in this pathway spin inversion and bond inversion are postulated as we have seen. And the difficulty here is that there is no way to predict which process is fast or slow. Now, let us try to understand the mechanism of insertion. In insertion you can see here this is the singlet carbene and with this CH, the CH2 will first form this transition state and eventually this bond between C and H breaks and this H ultimately comes to this CH2. So, that is how the insertion is taking place. In case of triplet carbene with the CH, first there is breaking of this CH bond, that is this formation of this carbon radical and CH3 radical, H dot is taken over CH2 carbene and then this CH3 dot and this C dot will be combining and that is how it is giving you this particular product, which is the inserted product. Let us talk about the general conclusions regarding the reactivity of carbenes. We can say intermolecular and intramolecular additions and insertions both can occur. However, wherever there is a possibility of intramolecular reactions, that will be preferred and intermolecular reactions may not occur. Intramolecular insertion reactions are more selective. The proximity of CH bond to the carbene center plays a major role in determining the product distribution. Addition reactions are almost 10 times faster than insertion into bonds. Let us now talk about carbenes. Is it an illusion or reality? Carbenes are postulated reactive intermediates which are known to chemists, but no carbene was ever isolated and its properties studied till 1911. In that year, one French chemist Ardungo, working in DuPont laboratory, reported the preparation and properties of a stable bottleable carbene, and its structure you can see as shown here. This carbene derivative has an imidazole ring and two bulky adamantine ring linked to nitrogen. It crystallizes from toluene as colorless rectangular solid with melting point of 240 to 241 degree centigrade. It is stable in the absence of oxygen and moisture, and it has been fully characterized by its elemental analysis, IR, 1H NMR spectra, and by single crystal X-ray diffraction methods. Several other types of stable carbenes have also been prepared and studied after that, and thus the existence of carbene is real and not a myth. Let us now look at some reactions which involve carbenes and carbenoids. For example, you can see here this preparation of tetracyanoethylene can be done through this particular carbene. Another reaction involves the preparation of ethyl orthoformate via the carbene, which is dichlorocarbene, as you can see here. Then there is isocyanide syn and carbyl amine reaction that you are already aware of. Here also you can see it goes via the carbene CCl2. Remer-Tiemann reaction again involves the dichlorocarbene as shown here. Then there is Arndt-Istad reaction where RCOCHN2, as it is heated, nitrogen goes and there is formation of in between carbene, and further it will be reacting with water, undergoes hydrolysis, gives you the higher carboxylic acid as compared to the starting one. Coming to the synthesis of cyclopropanes, this is a useful reaction in organic synthesis. A good method of adding CH2 unit to an alkene to give cyclopropane is to use CH2I2 and zinc copper. This method is commonly known as Simmons-Smith reaction. The active step is believed to be I plus ZnCH2I. Free CH2 is not involved. Simmons-Smith reaction has charge scope, wide applicability, and many functional groups can be present in the alkene. In preparation procedures, whereas CH2 is to be added to a double bond to form cyclopropane, free methylene is not used. Some other method which does not the reactive methylene itself. So, this is how you can see it will be in this Simmons-Smith reaction starting from cyclohexene, say for example, reacting with CH2I2 in the presence of zinc. This is how the removal of I2 takes place via this transition state, and there will be formation of this cyclopropane derivative. So, after understanding carbenes, their structures, their reactions, and how they behave in different medium, let us now try to understand what are nitrenes, what are their structures, and how do they behave in different conditions. If we talk about the definition of nitrene, nitrenes are the nitrogen analogues of carbenes, and most of the comments about carbenes also applies to them. Nitrenes are too reactive for isolation under ordinary conditions, although ab initio calculations show that nitrenes are more stable than carbenes with an enthalpy difference of 25 to 26 kilocalories per mole, and you can see the general structure of nitrene here. Here also it can be singlet or triplet which are represented here, and singlet again you can see here they will be both the unpaired electrons will be in the same orbital, but in case of triplet they will be in different orbitals. And such species, that is nitrenes, are also called as agenes, imidogen, imine, as a carbene. Nitrenes are postulated intermediates in certain reactions. Let us look at some significant difference between carbenes and nitrenes. If we compare the electronic state of the singlet and triplet nitrene, you can see in singlet the spins are paired and in triplet the spins are parallel. Looking at methods of generations of nitrenes, they can be generated from azides. The most common method of forming nitrenes is photolytic or thermal decomposition of azide, as you can see here, that is you have this HN3, when it is heated N2 will go and there will be formation of this NH nitrene. Similarly, in place of H, if you want to have some alkyl group, then starting from Rx you get alkyl azides, then on further heating or photolytic conditions the formation of Rn nitrene takes place when the nitrogen leaves. Similarly, we can start from phosgene and get this azidoformate, which on further decomposition will give you ethoxycarbonyl nitrene. Similarly, KN3 plus cyanogen chloride will give you cyanogen azide, which is highly explosive, but on further dissociation it gives this particular nitrene. Another example is the example of alpha elimination, and this method is not general and is of very limited application, where you can see this particular compound is treated with base and then we are doing the D, and here we are doing the removal of H and this OSO2 AR group, and we get this particular nitrene. Then there are oxidation reduction methods also for generation of nitrene. For example, you can see here this cyanamide will give you this particular nitrene. Similarly, you can see here with lead tetraacetate, this particular molecule will give you R2NN nitrene, and so here also you can see that there is the formation of phenyl nitrene, that is PHN, which is taking place. So, the great ability of phosphorus, as you can see in this reaction, is to combine with oxygen, and that is the driving force for this reaction. So, this is not similar to the method in carbene chemistry. So, there are these methods of generation of nitrene which are different than carbene chemistry. For example, if we look at this isocyanate simply on heating will have the removal of CO and then there is formation of Rn. So, this you can see is similar to the carbene chemistry, and oxygeridine similarly on treatment with photolytic condition you can get the formation of nitrene. Now, after the formation, let us look at the generalized reactions of nitrenes, and as you can see here, starting from nitrenes, they can be insertion between the CH bonds whereby you get the products like CNHR. They can be insertion between the NH bond where you get the products RNHR. It can add to the double bonds just like the carbenes and you get a 3-membered product which is aziridine. They can be reaction with alcohol where you get RONHR, and here even the aromatic compounds will react like with benzene. If you do the reaction, they can be ring expansion and azepine type of molecules will be formed. And let us consider some examples here. As you can see here, the first case here, starting with this molecule, there is first formation of this nitrene, and further when this is treated with water, we get this aldehyde after the cleavage of C double bond N or the hydrolysis of C double bond N. And on the other hand, through nitrene it can form this particular cyclic compound directly. Another example you can see here, the product composition here is on the insertion reaction, that is it can be lilic or vinylic or C1 position, and these are the various products which may arise by radical coupling through triplet nitrogen, which is this one, or you may get these aziridines, or they may be insertion between the CH bond or NH. Another example you can see is this cyanogen nitrene which is formed and it reacts with this cyclohexane derivative and there is formation of this product in 57% yield. Another example you can see is this adamantane with the nitrene, there will be CH insertion and the formation of this product. Another example you can see there is the intramolecular insertion into the ARH of ring B which takes place and you get this particular product. Another thing is starting from this optically active compound you get this product. You can notice there is a cyclization taking place after the nitrene is formed and the rearrangement, and this is around 40 to 45% yield of the product, and this can be further converted into this particular product by the treatment with trithoxy phosphorus molecule. Another example you can consider is this molecule which will give rise to another nitrene in between or intermediate, and it will further cyclize to give you this particular product. Let us now look at some reactions which involve nitrene as an intermediate. There are few examples of reaction which involve nitrene as intermediate. For example, you are already aware with the Curtius reaction, starting from RCON3 we get RCON as nitrene, and this further rearranges to give you RNCO, that is the alkyl isocyanates. Then there is the Hofmann bromide reaction, that is RCONH2 with bromine NaOH, where we get the acyl nitrene as the intermediate, which further rearranges to alkyl isocyanate, and further on hydrolysis we have the formation of primary amines. So dear students, let us now summarize what we have learnt in this module. In this module we have studied about carbenes and nitrenes. Carbenes are highly reactive species and practically have lifetime span considerably less than 1 second. The two non-bonded electrons of a carbene can be either paired or unpaired. If they are paired, the species is spectrally a singlet, and that is why it is called as singlet carbene, while if the two unpaired electrons appear as a triplet, that is they are in two different orbitals, they are in Pell spins, then it is a triplet and called as triplet carbene. And we have seen that the singlet carbene is sp2 hybridized carbon, and in triplet carbene the carbon is sp hybridized. The generation and reactivity of carbenes were studied in detail by the use of polar and isopolar approaches, and reactions involving carbenes were also studied, where we can broadly have three types of reactions like addition to double or triple bonds, insertion in the CH bonds as well as other bonds, and rearrangements. And many important reactions involving carbenes were discussed, including Riemann-Tiemann reaction. Then we discuss about nitrenes. They are the nitrogen analogues of carbenes, and most of the comments about carbenes also applies to them, with some exceptions that we have discussed. Nitrenes differ from carbenes in the term of electronic states and are generalized reactions. Important name reactions such as Curtius, Schmidt, Hofmann reactions were discussed, which involve nitrene as the intermediates.